Well, hi again. Tim coming at you with Lecture 11 of Physics 3113, Thermal Physics and Statistical Mechanics. In today's lecture, we're going to talk about bosons. In particular, we'll talk about the ideal Bose gas and the phenomenon of Bose-Einstein condensation. So we'll discuss Bose gas and low temperature behavior, the chemical potential, and we'll study how we get a large occupation of bosons in the ground state, and this will allow us to calculate the condensation temperature, or the critical temperature for Bose-Einstein condensation, and then we'll discuss a bit more about some of its properties. So, of course, when we have a collection of bosons, or an ideal Bose gas, that is a collection of non-interacting bosons, the properties are really quite different than those of the ideal Fermi gas. And of course, that's because of the statistics. And we'll see that at sufficiently low temperatures, bosons predominantly occupy the ground state at zero energy and zero momentum. So we'll see that below a critical temperature, which we call the Bose-Einstein condensation temperature, TC, the ground state occupancy becomes of order of n, the total number of bosons in the system. And in this range, the de Broglie wavelength, or the so-called thermal de Broglie wavelength, becomes macroscopically large. Around TC, it's such that the bosons start to overlap each other. And as we go to very, very low temperatures, then this wavelength becomes of order of the size of the container that you have the bosons in, like, for example, particles in a box. And so, and it's very interesting, this phenomenon of Bose-Einstein condensation, because the results we'll find here give a lot of insights into other types of condensation, in particular the superfluidity of helium-4, and then superconductivity of metals and superfluidity of helium-3. And these latter two types of superconductivity and superfluidity of helium-3 actually involve pairing of fermions that lead to bosonic behavior. We're not going to discuss that pairing in this course, but we'll just talk about non-interacting bosons and Bose-Einstein condensation, which gives a nice analogy and insights into these other systems, which are actually much more complicated. Okay, so previously we derived this Bose-Einstein distribution function, which is the mean number of bosons in some state of energy epsilon. And it has this form, 1 over e to the beta. Beta here is 1 over kBt. E to the beta times epsilon minus mu. Mu is the chemical potential. And we have the crucial difference from fermions of the -1 here. And we'll see that this chemical potential plays an important role in the temperature dependence of the ideal Bose gas. So we'll have to spend some time with this. Let's just write this. As we did before, we'll factor out this e to the minus beta mu, which is inverse lambda, this fugacity. So lambda is e to the beta mu. Let's just write it this way. And for now, I'll also drop this bracket notation, which means mean value, because we're going to be working. Imagine we're going to be working with a very large system, and we'll just ignore the fluctuations around that and take this as the number in the state. We'll be fine to do that for a large number of particles, as we've shown previously. Okay, so that's what we get if we write it this way. Now, it's quite similar to the situation with the ideal Fermi gas, right? We introduce the chemical potential because we imagine we have this grand partition function. That is, we have a system coupled to a heat bath and also a system with which it can exchange particles. And the way we do that is we define eventually we define the chemical potential in order to fix the mean total number of particles, which we'll call just n here, capital N. And remember, we did this for the Fermi gas as well, in particular t equals 0. And we get that by integrating over the density of states times this occupancy, or this Bose-Einstein distribution function. Of course, this formula is valid for fermions or bosons, but we'll use this function here for bosons. Now, at low temperatures, as you can, by looking at this occupancy, you could see this. is that the number of bosons in the ground state, if we set epsilon equals 0 here, this could become very, very large, yeah, because so we have to be a little bit careful when we evaluate this integral, and the reason is that remember we use the 3D particle in the box states, and we have this density of states that went like the square root of the energy, and of course you can see that this density of states G is 0 when epsilon equals 0. So that means in this integral that the states at 0 energy, are neglected if we just use this blindly. Now, usually that's not a problem, right? Let's see. So let's just write that again. So we have this equation, and of course, if this density of states goes like energy to the 1/2, then it's not going to get, we're not going to get any contribution from the states that sit exactly at 0. And usually that's not a problem for fermions because of the exclusion principle means, prevents multiple occupancy. So, missing one fermion down there when we go to a very, very large number is not really going to affect anything. It's going to be quite insignificant. But that's not the case with bosons because we could get a whole lot of particles down there at 0 energy. And so, you can imagine that you leave out the contribution there because we've gone from a sum to an integral essentially to get this density of states. Imagine when we're counting a lot of states that are close together. And so it's kind of an artifact of this. We just have to be a little bit careful with bosons. And as we'll see, what we need to do is separate out the number in the ground state that we'll call N0 here, because it can become really large, or the order of the number of particles. Now, so we have to kind of think about the chemical potential too, because it's really easy to see that the chemical potential mu has to be negative for bosons. We mentioned this in an earlier lecture, but let's just go through that again. So, the number in state epsilon must be, it's got to be positive or 0. It can't be negative, of course. And so there's the Bose-Einstein distribution of function. And so in order for this to be positive or 0, or positive, this epsilon has to be bigger than mu, right? Epsilon has to be bigger than mu, so this is positive here. I mean, because so let me just explain it. If this quantity were negative, right? If epsilon were less than mu, this quantity would be negative, and this factor would be less than 1, right? And that can't happen because then that would make the denominator negative. So this has to be true even when epsilon equals 0 at the ground state. And if epsilon equals 0 and mu has to be less than that, mu has to be 0, even for the ground state. So right. So we'll use this Bose-Einstein distribution to find an approximate expression for mu at low temperatures. Let's do this first. So we have for the ground state at epsilon equals 0, the occupancy, we're going to call it big N0 because that'll remind us that N, we're going to be interested in at low temperature when this N is big. So let's write big N0. And so at epsilon equals 0, of course, we just have this expression where we set epsilon equal to 0. And given our definition of the fugacity, we just have this, right? And if we solve this for the inverse fugacity, which let me remind you again what that is, it's the fugacity is e to the beta mu, so 1 over the fugacity e to the minus beta mu. We just solve this in terms of that, and we get 1 plus 1 over N0. And we see if we want N0 to be large, that means this term gets really, really close to 1. This is small. It's getting very, very close to 1. And if we want this to get very, very close to 1, then remember mu is negative, so beta mu must be small. And because mu is negative, this needs to be a small positive number. Because if it's a large positive number, this is going to be huge. So we need this term to be near 1, just slightly above 1. And that means this beta mu has to be, again, very, very small and close to 0. So if we expand the exponential here, so that is e to the, so if beta mu is really, really small, then I can expand the exponential and I get 1 minus beta mu. And then I can, and so for beta mu small, I just set 1 minus beta mu equal to this side. And so you can solve this, you see, and what you find is that, well, we write it now in terms of kBt, right? Beta is 1 over kBt. And we see that mu has to be negative and proportional to the temperature and divided by n0. So if, as we said, if n0 is very, very large, then mu is small and very close to 0. And it kind of goes linear to 0 with temperature. Now, as we'll see that, we imagine that as we get to very, very 0 temperature, we can see from the Bose distribution function that all the bosons are going to want to be down there at 0 energy. So if we assume that n0 goes to n, the total number of particles, as t goes to 0, it predicts that mu does this, that it goes to 0 linearly. It's negative, as it has to be, as we said, but it goes to 0 linearly from the negative side. So it goes like temperature, right? We'll see exactly how this goes later, but that's our argument. So we know, so in conclusion, mu has to be negative, and it gets very, very close to 0 as we go to low temperature. Okay? And that we got by assuming that a large number of particles were in the ground state, which we know has to be because of the Bose-Einstein distribution function. Okay? There we go. Well, so we saw then that the number of bosons in the ground state, the 0 energy, becomes very large as the temperature is lowered. And we worked out what that meant for the chemical potential. Well, what about the number of bosons in other states, in states other than the ground state? So let's denote this N sub E for excited bosons. What about the number that's not the number not in the ground state? Well, this of course will just be given by the integral that we wrote down before. We'll just call it N sub E here, but it's exactly the same integral because, as we said, this neglects the number that are sitting down there at 0 energy because this density of states is 0 at 0. So we can calculate the number in the excited state in the usual way by doing this integral. And once again, let's assume single particle states, that is, particles in the box states, where we derived this density of states in prior lectures. So this density of states has nothing to do, of course, with whether the particles are bosons or fermions. It's just the levels that you get from quantizing particles in a box. And so we had this expression. It goes like square root of epsilon, and it has this prefactor. And it's proportional to the volume, of course. And so we can do that integral, and so now we have integral like we saw for fermions, except we're going from 0 to infinity here of this function, right? Well, so that's the number of particles not in the ground. So now, like we said, if we didn't have to worry about the particles in the ground state, we could say, this is the total number of particles. So what if let's do a kind of thought experiment. What if we wanted to keep all the total number of particles in states other than the ground state? That is, we wanted the total number of particles to be this number. And we remember we can always adjust. We always define the chemical potential by this essentially constraint given by the number of particles. So let's suppose that we wanted all the number of particles up there. Let's look at this integral, and suppose we lower the temperature. So we have some number of particles, and we're not at low temperature where mu is completely arbitrary close to 0. It's some value. Mu is some value, and suppose we then lower the temperature, and what would he have to do to keep N the same, right? Well, you look at this, and you say, well, as I lower the temperature, beta's getting larger, right? And so this factor this factor here is starting to get larger, and then, so the denominator is getting larger because this factor is getting larger, and this thing in the integral is getting smaller. And if I want to keep in the same value, I've got to change something here. So I've got to actually change this factor to compensate for the beta thing making it smaller. And the way to do that is, of course, to adjust the chemical potential. And the way to do that is, if we lower the temperature, mu, remember, which is negative, we would have to increase mu. So make it less negative, right? And so this term, so if beta is getting larger, we need to make this term smaller, which means making mu closer to 0. Okay? If we wanted to keep this fixed. And this, and what you see then is that the temperature can only go so low in this situation because we can't arbitrarily make mu, we can't make mu positive. So if we need to push it closer and closer to 0, at some point, we can't push it beyond 0. And so if we keep lowering the temperature, then we can't make this factor, we can't compensate this factor to keep n fixed, right? So this actually defines a critical temperature below which we can't keep n fixed, and that critical temperature can be found by doing this, of course, when we set mu equal to 0. So let's define that. So in other words, the critical temperature is going to be defined by the value of this integral with mu set to 0. And so we can do that integral, right? I've put here just the constants here, and then we have this integral with mu set to 0, and I've written it instead of beta, I've just written it kBT C, because that's the critical temperature. And so we could do this integral, but it's actually helpful to change our variable of integration to some dimensionless x. So we have in the exponent here we epsilon over kBT C. So let's call that x, which is a dimensionless variable, and we'll change the integration variable to this x. And of course that brings out that this factor, this is proportional to epsilon 1 over kBTC. And of course, if we change variables to x here, we get essentially x to the power 1 plus 1/2 is 3/2. So we get this constant, of course, the 3/2 out here. And then we have this integral left over here. So so I'll write this integral by taking these constants, and I'll take out another factor here of 2 over root pi. So I'll just kind of I've changed variable. This is dimensionless integral, and I brought everything aside. But I'm just going to put back this 2 over root pi, and it'll become clear why I do that in a minute. And so we have it this form. So basically, I mean, that's all there is really to it, because if you think about this, this integral here is a definite integral. It's an integral from 0 to infinity of some x. There's no other constants or anything here. So, this integral is just going to be some constant, right? And we could find, I mean, if you want to, you can find that numerically. It's just, so this is just a constant, this definite integral. And the reason why I've written it like this is because this integral is actually recognized and has a name, and we'll find that. But at this point, you could say, okay, that's some constant. Okay? Let me think of that a bit. Okay, that's what we had. And so I wrote it this way because one recognizes this integral, and it's one that's found in the definition of the so-called Riemann Zeta function. You may have had that in another course. And the Riemann Zeta function is a function of z. This is zeta of z. Okay, it's 1 over this gamma of z, which is another definite integral, so another number, times this integral, right? And so you can see that our integral here is basically z equals 3/2, right? And so, and gamma of z's defined through this integral here, but you always know it's actually a definite integral. It's just a number as well. So basically, this integral here is equal to 2 over square root of pi times the zeta function of 3/2 times the gamma function of 3/2. And the gamma function of 3/2 is known. It's just this. You can do this integral. And if you go off to a program, and it's a good enough program, it'll find that. But it's actually square root of pi over 2, which is why I pulled this factor out. And this Riemann zeta function here of 3/2 is just it's a irrational number. So we'll just take a few decimal places. It's just this value, 2.6124, and so forth. Okay, so that's why I wrote that. So now we have this result kind of written out quite easily. This, like I said, this is just a constant. This integral becomes this constant here, the zeta function of 3/2, and this is just from before. So actually, and I've just moved the v over here. So basically, TC is defined now by this equation that we got. Okay. Let's write it for TC. It's just that. Okay. So we found this critical temperature, where mu equals 0, where the number of particles essentially in the excited state. We couldn't fix the number of particles in the excited state, or we couldn't fix the total number of particles if we wanted to do that in all the states except for the ground state. So what does that mean? That means below this temperature we must have a lot of particles starting to go into the ground state at epsilon 0, just like we sort of argued at the beginning of this lecture. Oh, by the way, I should say you could easily go through the same integral and put a factor of s, out front here, and you would just have the s downstairs as well. So to summarize, then, for T less than some critical temperature given by this expression, we can't keep all in particles out of the ground state by adjusting the chemical potential, because the most it can be is fixed at 0. So that defines this critical temperature. So to make progress here, we're going to have to separate out the contributions and to see what's going on. And so we do this by writing, of course, n equals n0 plus the number in the ground state, energy 0, plus the number in excited state. And as we had before, this number for epsilon equals 0 is just that term, and the number in excited state is just this thing we figured out before, except at some arbitrary t, right? So this is a function. So this is what we get for arbitrary t below Tc. Well, I mean, this expression works for arbitrary t, but we're going to look for t below Tc. So, and as we found before, n0 is just, of course, this factor, and the excited part is just this integral we did here with kt. I left out the b, but kbt. Okay? And then, and we also note that above Tc, by looking at this expression, above Tc, we'll realize that this n0 is negligible, and we can admit it. And mu is given by this, this equation. We can ignore, for T above this critical temperature, what we're saying essentially is that we can ignore the small occupancy of the ground state and just use this expression. That's what we're saying. But below Tc, this chemical potential stays really, really very close to 0. And we'll see how close a bit later, but that's what our arguments or our calculations are telling us. So now let's look at the number in the excited state for some T less than Tc, which we can think by taking mu equals 0 in this expression, because mu below Tc is extremely close to 0. And so again, we have this expression, again, with now T some arbitrary thing, and we have all these constants. And I mean, it's really the same calculation we found we used to find Tc by wanting this to be the total number of particles. But now we're going to say it's the number in excited state, and it depends on temperature. And basically, we could work this out, and we would see how the number of excited states depend on T and TC, because TC, is some combination. Well, if you remember what TC is, it's this factor here, right? You could completely do this integral again as it stands now, and then you would find that the expression you get has a bunch of constants that you could find are related to TC, the TC found before. And you can do that if you want. But there's kind of this cute trick we can play again with this problem as well. We can write the density of states in terms of this TC, by doing this trick we used before. It's just say that, well, it's some constant times this dependence that we had. And then we go back to the equation for TC, and we can actually find what that constant is in terms of TC instead of in terms of all these factors here, basically. And lo and behold, I'm not going to go through. It's very easy. It's the same integral we've done before and so forth. And so you can find that A expressed as TC instead of volume and mass and H, all that stuff is something like it's just N over KBTC to 3/2. Of course, that should write plus times these constants again. So in that form, it's very easy to find TC. We just do this integral, and of course, that makes the whole situation very simple. We have this thing that we recognize to give with this integral again, and we change variables, and this gets canceled. This integral, once we change variables, this cancels out that. So this integral equals that in the denominator. And in the end, we get a pretty simple expression this way. I mean, like I said, you could do it the long way if you want, and you just get the same thing. You just have to do a bit more algebra. And what we see is a simple kind of result that the number in the excited state below TC, so we're at T below TC, is the total number times T over TC to the 3/2 power. Okay? That's from these terms. Because all this cancels out in the end. Okay. And then, so what if we divide this by n? That's the fraction of particles in the excited states. It's just T over TC to the 3/2. And so the remaining fraction must be in the ground state. That is the fraction of particles n0 over n in the ground state must be 1 minus this fraction. So we can write it out as n0 over n equals 1 minus this T over TC to the 3/2 power. So this tells us, quantitatively what we had argued was happening, that below TC we get a large number of particles in the ground state. The fractional occupancy gets very, very large, which means we have a large number in the ground state until we get to T equals 0 when all the particles are in the ground state. But this actually tells us the form of that. And so that's, so we plot that. Of course, it looks like this. So this number in the ground state, is infinitesimally small above here, right? And in the thermodynamic limit, in the limit where n goes to infinity, it really is 0 up here, and it goes like this below. That's this power law we predicted: 1 minus T over TC squared, or TC to the 3/2. Okay. Yeah, so for T greater than TC, the number of particles in this ground state is actually negligible. And in fact, for n, the total number of particles going to infinity, it really does go to 0 there. And this becomes very sharp, and yeah. So below TC, the number of ground state increases rapidly, and this is a phenomenon of what's called Bose-Einstein condensation. Okay, now this growth that starts out from 0 essentially tells us that the Bose-Einstein condensation is a phase transition, and moreover, it's a continuous phase transition, also known as a second-order phase transition. In continuous or second-order phase transitions, you have an object called the order parameter, which grows from 0, right? And so this condensate fraction is, for this type of condensation, is the order parameter. And another example of order parameter, by the way, is the sort of magnetization per spin, technically. So this is like fraction, and this is sort of like magnetization per spin for the Ising model, spin model, below its critical temperature. Both these are examples of, one, second order phase transitions, and both have a typical so-called order parameter, because you get some sort of ordering. And here the ordering is that the large number of particles in the same state. Okay? Right. So, and once again, we have to mention that particles in the condensate have zero energy and zero momentum. And because of this latter property, they don't contribute to pressure or viscosity. So both these, well, pressure is obviously, with viscosity, because there's no momentum, right? Pressure becomes because you have particles bumping into the walls of your container, so you're changing the momentum. So, and viscosity also involves transport of momentum. So viscosity means, so if you have a fluid and you try to drag something for the fluid, then you have some resistance. And so obviously putting a spoon through honey, there's more viscosity than dragging a spoon through water or alcohol or something. And so one property of this condensation, Bose-Einstein condensation, or any sort of superfluid actually, is that it has zero viscosity. So there's no resistance to moving objects for it. And I mean, also, if you have a glass of a liquid and you spin it around and around, you basically, some of the liquid sticks to the walls and you get this little vortex. There's lots of really interesting properties that Bose-Einstein condensates and also other superfluids have because of these properties, and we might get to discuss a few of those in a later lecture. Okay, well, that's it for our introduction to Bose-Einstein condensation. In the next lecture, we'll discuss a few more properties of it and some other aspects of that. So see you next time.